Talking chapter 15, I think. And we're talking about solutions. And last time we really got into concentrations. And we talked about several types of concentrations. But again, one of the most common sort of concentration units that we use is molarity. And molarity is abbreviated with the big M, and it does stand for moles of solute divided by liters of solution, or more commonly, just molarity is moles divided by liters. Remember, this is sort of like a formula. We do use it really to solve for one of those three things. So if you again want moles, it is liters times molarity. If you want liters, it is moles divided by the molarity. One of the most important things I think we talked about is, in terms of sort of molarity, is a couple of things. First off, when you do use molarity by itself, the volume always has to be in liters for everything to sort of cancel out correctly. And that means usually you have to do sort of a milliliter to liter conversion is very common. So again, a reminder, 1,000 milliliters is 1 liter. So that's used a lot. Also, moles. Sometimes you do need to calculate the moles. So again, grams to moles using the molar mass from the periodic table is also another very common sort of conversion that we use. Thank you. In addition, when you do have the molarity given to you, as I mentioned a lot last time, it's really a good idea to sort of get rid of the big M and sort of put both units in so that you can see them, and also take a more dimensional analysis approach with the calculation. If you do that, you don't even really have to worry about rearranging this equation. You could just kind of do dimensional analysis. So when you have something like that, that is 3.25 moles of sodium chloride per liter. The number always stays with the moles part, and it's always 1 liter basically when you do that. And you can really use that as a conversion factor. You can put the liters up on top and the 3.25 moles, say, of sodium chloride in this example on the bottom. So once again, you could kind of use it as a conversion factor and take a dimensional analysis approach. It's a really good idea to do that because, as I mentioned before, it is a very common error that a lot of people make, which is they just really don't even think about the volume part of it. They just think about the M and they think moles, and they're not even sure where the volume is or where it should be. So again, if you kind of get rid of that big M, put both of those units there, you can visually see both of those things, and it's a really good way to kind of do these type of problems, especially if you have the molarity given to you. Um, we also talk about dilution. Dilution is when we basically take a more concentrated solution and we add more solvent. So a lot of times that's water. And when we add more water, something like that, which is a solvent, we will lower the molarity of it. And there is a dilution equation, which is M1V1 equals M2V2. And this is usually molarity and volume before the dilution. This is molarity and volume after the dilution. And remember that when you dilute something, the moles of solute that's present does not change. So just the amount of solvent changes. And that is why the molarity goes down, because a reminder that a solution is the solute plus the solvent. So when you do a dilution, you're really adding more solvent, which increases this bottom part of the molarity formula. And because the bottom part's on a larger number, the molarity will go down when you basically divide, obviously, a smaller number by a larger number. You'll get a smaller molarity number in that case. There is a more generic version that sometimes people use for dilution, which is C1V1 equals C2V2. C there is just a generic concentration unit. So a lot of times people use M1V1 equals M2V2 because molarity is the most common unit of concentration. But technically speaking, you can use any type of concentration unit like percent mass to mass. So we also talked about percent mass volume, whatever it may be. So that is okay. Also remember that if you happen to be using this formula here, and only when you're using this formula probably, in most cases, if you want to, you can leave the volume in milliliters. It will work out okay. You can use milliliters on both sides as long as the volume is the same units on both sides. It'll be okay. Um, if you use milliliters on one of the volumes and you're solving for a volume, you'll just end up with milliliters. You could also convert it to liters as well. So you do have a little bit of option if you're specifically using this equation. But if you're doing this calculation here, it does need to definitely 100% of the time be in liters, so everything cancels out correctly. Any questions on any of that stuff there? All right, so I think we did one dilution problem, so let's take a look at another one here. So why don't you take a moment? What is the volume of water that's needed to prepare 500 milliliters of a 0.25 molar calcium nitrate solution? Okay, let's take a look. So once again, as I mentioned before, we want to make a 500 milliliter 0.25 molar solution of calcium nitrate from a 5 molar calcium nitrate solution. So they're both calcium nitrates. So there's no reaction or anything happening. This is just a dilution. So once again, we have a bottle of calcium nitrate over here, and it has obviously a higher molarity, and we want to make a new sort of container that has a volume of 500 milliliters and 0.25 molar in terms of concentration. So this is basically M1. We don't have V1. This would be V2, and this would be M2. Now, typically, the more dilute one is the twos, and the more concentrated ones, the ones. It really doesn't matter as long as you keep the numbers together, whichever ones you call ones and twos, as long as you keep the volume and molarity together that goes together. So in this case, we'll do M1V1. Write that right. There you go. M2V2. Here we are going to solve for V1, so we're going to divide that to the other side. That's going to give us V1 is equal to M2V2 M1. Putting in our numbers here, M2 is 0.25 molar, 500 milliliters. Once again, because I'm using specifically this equation or this formula, I do not need to convert it into liters. If you want to, you can. The only difference here is your answer will be in liters rather than milliliters. So you're okay to leave it here. And the reason you are is just because of this molarity on top and bottom cancel, and that leaves us milliliters as our answer. And we will end up here with something 25 milliliters. Now, that 25 milliliters is 25 milliliters of calcium nitrate that we're going to take out of this container, and that's what we're going to put into our new container is 25 milliliters of that guy. Remember here, though, that very commonly on dilution problems, they're interested in how much water you need to add with it. So the volume of water is typically V2 minus V1. So we'll take our V2, which is 500 milliliters, the total volume we want. We obviously have already put in there 25 milliliters of our more concentrated solution. That means that we would need to add in there about 475 milliliters of water with it. And if we put in there the 475 milliliters of water with it, we would end up with 475 plus 25 gives us our grand total of 500 milliliters. And once again, here we would give it a mixy there, and we would now have a solution that is 0.25 molar. So again, it's really important, especially with dilution problems. It's a very common question, kind of like how you make the solution, how much water do you need to add. So sometimes people just leave it as 25 in this case, rather than sort of answering that question. Any questions on it there? All right, so that is dilution. So what we're going to talk about next is actually putting together stoichiometry and solution, uh, molarity and stuff like that. So uh, we can do solution stoichiometry problems, and much like most stoichiometry problems, it's the same stuff that we've been talking about over the semester. We're still going to balance the equation. We're going to convert everybody into moles. If it is a limiting reagent problem, we'll figure out what is the limiting reagent. If it's not, we don't have to worry about it. We'll calculate moles and convert moles to some other unit. So these are our same sort of four basic steps that we've used along the way. The difference here a lot of times with solution stoichiometry is at this step, instead of doing grams to moles, which we may sometimes still do, oftentimes we will use molarity and we will solve for moles by taking liters times molarity. So that's a very common sort of substitution in there. It's just kind of using the volume and the molarity that's given to us to get to moles rather than using grams in the periodic table to do so. And really, the only other difference is at the end here. Again, a lot of times we may actually calculate the molarity. So we may just use the molarity formula to calculate it. In addition, maybe we know the molarity and we'll know the moles. So maybe we'll solve for something like liters sometimes as well. So I would say again, kind of step two and the last step is where we oftentimes will incorporate molarity into the stoichiometry part. Everything else is the same. You just got to do a basic stoichiometry problem, or if it is a limiting reagent problem, you just got to determine the limiting reagent and continue on like normal. Remember, regardless of what units you're given, if you can get to moles from based on the information given to you of everybody in the reactant side, then it is a limiting reagent problem. So let's take a look at one here together. We want to calculate the mass of solid sodium sulfate that must be added to 250 milliliters of a zero point 0.2 molar solution of barium nitrate to precipitate all the barium ions as barium sulfate. We want to calculate the mass of barium sulfate also that we're forming. So we want to sort of write our formula. In this case, we have everything given to us in words. So we want to calculate the mass of sodium sulfate that must be added. So sodium sulfate is Na2SO4, as that is sodium plus 1 and sulfate minus 2. Must be added to barium nitrate. Barium is plus 2, nitrate is minus 1. So when you put that together properly, you end up with something that looks like this, BaNO3 2. This should be recognizable to you in a type of reaction that is two ionic compounds, which means this is a double displacement reaction. So these two guys are going to switch partners on the other side, and we're going to form barium sulfate, which barium is plus 2, sulfate's minus 2, which means it will make barium sulfate. And sodium is plus 1, and nitrate is minus 1, which means we will get sodium nitrate that looks like this. We will not get Na2NO3 Yes, so remember, you want to write the right formulas first, and then you should balance it. So these are the proper guys. Remember that when you're doing that, you just want to take a look at the basic ions that are present. And these are the basic ions that are present here. And these are the guys that come together, and these are the guys that come together properly to make what's on the product side. Now that we do have the equation, it is not balanced, so we definitely cannot do stoichiometry as we know without it being balanced. So to balance it up, perhaps we need a 2 there, and I think that might actually do it. Let's see. 2 sodiums, 2 nitrates, a barium, and a sulfate. So I think we're balanced at that point. So once again, remember, if you have it in words, proper formulas, then balance with the coefficients. Any questions on that there? All right, so in this particular case, actually, this is solid, actually. Cool. So we're taking 250 milliliters of 0.2 molar barium nitrate. So I think I'll just borrow that there. 250 and 0.2. So what we have on this case is 250 milliliters of 0.2 molar barium nitrate. And we want to know how much sodium sulfate we will need to put with that, and also how much product we will produce. So I'm just going to erase some of this here, give me a little bit more room. All right, so we actually have two questions here, which is basically question number 1, or A, is how many grams of this guy, And question B is basically how many grams of that guy. So we're just going to start with the first one, which is A. So when I look at this here and I want to know how many grams of sodium sulfate, I could look at what's given to me. And once again, what's given to me is enough information to get to moles of this guy. And that is all that's given to me. So this is a basic stoichiometry problem. This is not a limiting reagent problem or anything like that, because obviously we're looking for one of our reactants anyways. So that's where we're going to start. So from the milliliters and molarity, I know that molarity is moles per liter. I definitely have the molarity. I definitely have the volume. So once again, I can rearrange that and solve for the moles. Remember that I'm going to turn my molarity that was given to me into really just a conversion factor. So that is 0.2 moles over a liter of barium nitrate. Or I could use it the other way. I could flip it around and do the liters on top and the 0.2 moles of barium nitrate on the bottom. And again, I'm going to take a more dimensional analysis approach here to sort of do what I need to do. We also need to convert our volume into liters. So that is 250 milliliters. 1,000 milliliters is a liter. That gives me 0.25 liters. All right, so without even worrying about sort of the formula for molarity, taking a dimensional analysis sort of approach here, I got my liters. All I have to remember on that is opposite location for the liters. So I'm going to put liters on the bottom, zero point 0.2 moles of barium nitrate up on top. And that's going to give me here 0.25 times 0.2, 0.05 moles of barium nitrate. Now, ultimately, I am interested in this guy and one of my answers. So now I'm going to do the mole-to-mole relationship. This is kind of like step number 2. Step number 3, going to the equation. It is a 1 mole of sodium sulfate to 1 mole of barium nitrate. And that is the stoichiometry from the equation. That is the coefficients here. A 1-to-1 relationship between them from the coefficient. Remember, we're just going to use that as a conversion factor. So 0.05 moles of barium nitrate. That's going to give us, from the equation, 1 mole barium nitrate is 1 mole of sodium sulfate. I think I could do the math on that. That's going to be 0.05 moles of sodium sulfate. Now that's close to what I want, but I do want grams. So our 4th step here is going to use the molar mass of sodium sulfate. So that is 2 sodiums at 2299 plus a sulfur at 3207 plus 4 oxygens at 16 each gives us from the periodic table 142.1 grams per mole as the molar mass. And if I do that, I will see here and end up with about 7.1 grams of sodium sulfate is needed to react with our barium nitrate. And again, this is still the same basic 4 steps that we've done previously. Balance the equation, convert to moles, just a different way of converting to moles using liters of molarity. Mole-to-mole relationship, and moles to some other unit using our grams per mole from the periodic table. Any questions first off on that part of it there? Now, in this particular question, there's actually 2 parts to it. The second part was how many grams of our product would we make? And by the way, since this sodium sulfate is not a product, this would not be a yield because a yield could only be a product. So we could actually do our same 4 steps, and we actually have done 2 of them so far. We have step number 1, which is the equation. We have step number 2, which is convert to moles. So really at this point, we could pick up with that problem right about here, because that's going to be the exact same step here for B. So number three is our mole-to-mole relationship between the sodium sulfate and the barium sulfate, and it is also a one-to-one relationship, which means 1 mole of sodium sulfate will give me 1 mole of barium sulfate. And that means I'll take my 0.05 moles of barium nitrate. I will use my stoichiometry here. 1 mole of barium nitrate gives me 1 mole of my product here, which is barium sulfate. And that gives me 0.05 moles of barium sulfate. Again, we are looking for grams, so we do have to do that last step there and convert to moles. And let's see here. Barium is 137.3, I think, something like that. 137.3. There's a sulfur, 3207, and for barium sulfate, 4 oxygens, which is 16. So if you go to the periodic table and calculate the molar mass of barium sulfate, you get something like 233.4 grams per mole of barium sulfate, which if you times it by 0.05 gets you about 11.7 grams of barium sulfate was formed. Since that is a product, that would be the theoretical yield in this case. So that would be the theoretical yield in this particular case. And obviously this would be our fourth step along the way. So even though there's two kind of separate calculations in here, we still did for the second one, balance equation, convert to moles, mole to mole relationship, and our product there, which is our theoretical yield, as opposed to our first one there that we ended up over here. Yeah. Any questions on any of those steps? So hopefully, again, you can see as we've gone through these different chapters, stoichiometry is always still really the same 4 steps. You just got to incorporate how you get to moles and what you do with those moles at the end of the problem. In a gas problem, you use a gas law, and sort of solution stoichiometry, a lot of times you will use molarity along the way. Any questions on any of those steps there? All right, so why don't you maybe try one here? I think maybe. So why don't you try this one? Calculate the mass of white solid calcium carbonate that forms when 25 milliliters of 0.1 molar calcium nitrate is mixed with 20 milliliters of 0.15 molar sodium carbonate. So take a step through it, go through our stoichiometry steps, our 4 steps, determine if it's a limiting reagent or not. And I'm going to give you some numbers that might be helpful at the end there. Calcium 4008, carbon 12.01, and oxygen 16. Okay, so let's take a look and see how you're doing. So we want the mass of solid calcium carbonate that forms from the mixture, basically of so much calcium nitrate with some sodium carbonate. So this is definitely a stoichiometry problem. So just going through our steps here, we're going to get our equation. So we do have our calcium nitrate reacting with our sodium carbonate. And once again, you should recognize this as a double displacement reaction. We're going to basically switch partners here on the other side. So I'll just go below since I just kind of run into it. So calcium nitrate plus our sodium carbonate. And again, when we switch partners, that is calcium with a +2 charge and carbonate with a -2 charge, which means when they come together, we just need one of each to make that solid. And again, here, the sodium and the nitrate will come together. That is sodium with a +1 charge and nitrate with a -1 charge. So once again, the formula does look like this. It does not look like, again, Na2NO3 2. At this point, we definitely want to balance. So looks like perhaps a 2 there. And I think, again, that might actually do it there. So I think we're in business. All right. So in this particular case, if we kind of look and see what's given to us, we got 25 milliliters of our calcium nitrate. And we do have the molarity of it, zero point 0.1 moles per liter. Again, I'm just going to convert it into both units there. And for our sodium carbonate, we got 20 milliliters, and it has a molarity of 0.15. Again, going to convert it into moles per liter, getting rid of the big M there so that we can see both units. So the first thing I want to determine is, obviously we need to convert to moles, which we definitely could get moles of this guy. We definitely, from that information, could get to moles of this guy. And because we could get to moles of each of these reactants, that should tell us that this is a limiting reagent type problem. So again, you always have to be sort of on the lookout whether or not you have a limiting reagent sort of situation happening. And that's exactly how you determine it. If you can get the moles of each reactant based on what's given to you, then it is a limiting reagent problem. So that's just something we got to keep in our head here, that we at some point need to figure out the limiting reagent. But the second step's still going to be the same. We're going to convert these guys into moles. And again, we do have to convert our volume into liters here. So 0.025 liters is 25 milliliters divided by 1,000. We're going to use the molarity just like it is, 0.1 moles per liter of calcium nitrate. And that's going to give us our moles of calcium nitrate, which is 0.025 times 0.1 gives us 0.0025 moles of calcium nitrate. I'm going to do the exact same calculation with my other reactant, also converting it into liters by dividing by 1,000 gives me 0.02 liters. Going to times it by the molarity of the sodium carbonate, which is 0.15 moles per liter of our sodium carbonate. And that's going to get us here 0.02 times 0.15, 0.003 molar here, 0.003 moles of sodium carbonate. So remember, in this case, because this is a limiting reagent type situation, these are your starting amounts of each of those guys. First off, any questions on that there? So again, we talked about a couple different ways, or a few different ways that you could kind of do limiting reagent problems. But here I'm going to figure out how much of the, so I'm going to do my limiting reagent calculation right here, which is how much of the sodium carbonate is needed. So to do that, I'm going to take my starting moles of calcium nitrate, which is 0.0025 moles of calcium nitrate. I am then going to do the mole to mole relationship between calcium nitrate and the sodium carbonate, which is a 1-to-1 relationship from the equation. So 1 mole of calcium nitrate gives me 1 mole of sodium carbonate. And again, that's the calculation that helps us determine which one's the limiting reagent. That would tell us that we need 0.0025 moles of sodium carbonate is needed in this case to use up all of our calcium nitrate. Remember that what we're comparing is how much is needed of the sodium carbonate to how much we had to start with. And in this case, we had 0.003 and we only need 0.0025. So we do have enough. And that means that this guy is my excess reagent. And that would mean by default that the other one is my limiting reagent. So remember, you do have to determine which one's the limiting reagent through some type of calculation. It is not just the smallest number of moles. So it's actually a calculation based sort of situation that you need to do. First off, any questions on that there? All right, now that we've done that, we can really finish the rest of the problem, which is we're going to take our third one, which is we're going to use our limiting reagent moles. So 0.0025 moles of our limiting reagent, which was calcium nitrate. We're now going to go to our product. So it is a 1-to-1 relationship there. They obviously are not all 1-to-1. We happen to hit a bunch of them in these problems, but 1 mole of calcium nitrate gives us 1 mole of calcium carbonate. And that's going to give us 0.0025 moles of calcium carbonate. And we do want to know how many grams, so we're going to go to the molar mass here and calculate the molar mass of calcium carbonate. And if we do that, that's 1 calcium at 4008 plus a carbon at 1201 plus 3 times 16 for our oxygens. That's 100.1 grams per mole. So our last step here, 100.1 grams per mole of calcium carbonate from the periodic table will yield us here 0.25 grams of calcium carbonate would be produced in this case. And that again would be a theoretical yield, as that is a product in this case. So once again, our same sort of 4 steps that we've done in previous stoichiometry problems. We got our balanced equation here. We converted to moles using volume and molarity. We did our limiting reagent calculation because we needed to. We used our limiting reagent and did our mole to mole relationship from the equation. And our last step here, we're just using molar mass to get ourselves 2 grams. Yeah. Any questions on any of those steps there? Okay. So hopefully you've seen some patterns that, again, you've seen previously, just incorporating molarity and volume and moles to get parts of these calculations. All right. The next thing we're going to talk about is sort of the lab that we did last week as well, and we talked about it there, which is neutralization reactions. And when we take a strong acid plus a strong base, we usually get 2 things, which is a salt and water. Water obviously being H2O. A salt's an ionic compound. And remember, this type of reaction is a double displacement. The H plus from the acid and the OH minus from the base is what comes together to make the water. So if you had something like hydrochloric acid, like you did in that titration, plus some sodium hydroxide, that is a strong acid and strong base. Strong acid, strong base. Also a double displacement reaction. So we're just going to switch partners here, basically. And again, that's going to make sodium chloride and water. And that, again, is our salt and obviously our water in this case. Once again, in this situation, that is always pretty much how water is made. The H from the acid, the OH from the base is basically where our water basically ends up. And obviously our salt ends up as to what is left over there. Our sodium ion and our chloride ion in this particular case is how we get to our salts as we sort of rearrange it. So that is our molecular equation. Our total ionic equation would be something like H plus Cl minus plus some sodium ion, hydroxide ion, sodium ion, and chloride ion here. Plus our water, which stays together because it's a liquid, spectator ions, sodium and chloride on both sides, and that yields us our water here, which is our neutralization reaction. So one of the most common ways that we sort of oftentimes will do a neutralization reaction is very common, like we did in the experiment there, which is titration. So a lot of times we will use titrations to do acid-base neutralization reactions. And as you know from a titration, as we did, we basically use something like a burette and we add one to the other. So, for example, we could add our base to our acid, or you could do it the other way around as well. You could put the acid up on top in the burette and you could add it to the base. So you could do it really either way of titration. Doesn't necessarily always has to be the base up on top. But we continue to do this until we reach what is known as the equivalence point. And remember, in an acid-base titration, that is the point where the moles of the acid equals the moles of the base. So that's the exact point where pretty much the reaction is over. And remember that we can see that using an indicator like you did there, like phenolphthalein. And remember, it changes color near the equivalence point. So your indicator changes color near the equivalence point, as you saw that particular one, phenolphthalein, changes from colorless to pink, light pink to dark pink, depending on where you ended up. And again, that's just a visual indication that you should stop. Typically in a titration, as we talked about, you have like a known solution and an unknown solution. So what that means is typically in the known solution, you know the molarity of it and you know the volume you used. For the unknown, maybe you just know the volume that you used, or maybe you might even know the molarity in some cases, but there's something you don't know about the unknown. And we can use stoichiometry really to answer these questions. And it's still the same steps, again, just using that molarity and volume. Any questions on that there? All right, so let's take a look at one here. And what volume of 0.1 molar nitric acid is needed to neutralize 45 milliliters of 0.55 molar KOH? Again, if you come across a question like this, it's kind of like a titration question. We have acid and bases. It really is still solution stoichiometry. So we're going to start with our normal step here in stoichiometry, which is, again, we need an equation. So we have nitric acid, which is a strong acid, reacting with potassium hydroxide, which is a strong base. Remember that acid and base reactions fall under double displacement reactions. So positive, negative, and again, we're just going to switch partners here. And that's going to give us water that's definitely going to be formed. And again, our salt, which in this case is potassium nitrate. Potassium is +1, nitrate is -1. So that is what you get. So again, hydrogen from the acid, OH from the base, that is where our water comes from. And once again, as well, our salt comes from the potassium and the nitrate coming together. So again, that is how we get to there. We do want to make sure it's balanced, and I think in this particular case, I think we are actually balanced at this point. So it is balanced in this case. The next step is we want to kind of convert what they gave us to moles, and we want to also determine, is this a limiting reagent type situation? So let's take a look at that there and see. So definitely in this problem, we are looking for the volume here of nitric acid. We do know the molarity of it, which is 0.15 moles per liter. Again, I'm getting rid of the big M and showing both units. For the potassium hydroxide, we have 45 milliliters of it, and we have the molarity of 0.55 moles per liter. Once again, getting rid of the big M. So the first question of, is this a limiting reagent problem? The answer is no, because this guy here is the only thing we could get moles from. We cannot obviously get moles because we were missing the volume. So this is just a basic stoichiometry problem at this point. And if we think about molarity for the nitric acid, I have the molarity given to us. I am looking for the volume. So once again here, the one thing I'm missing to solve the problem is moles of nitric acid. And that's really where the stoichiometry part is going to come into play. We're going to use stoichiometry to figure out the moles of the nitric acid, and we're going to do that based off of our potassium hydroxide here. So step number 2, we're going to take the only thing we could get moles from. Once again, we do need to convert this into liters. So we got to divide that by 1,000, and that will give us 0.045 liters. So again, you definitely, as we talked about, molarity and volume. Volume needs to be in liters. So again, 1,000 milliliters is a liter, 0.045 liters. Again, using my molarity as a conversion factor, 0.55 moles per liter of KOH. Liters are going to cancel, going to leave me with moles. And we will end up with 0.045 times 0.55. Going to end up here with 0.02475 moles of KOH. So remember, though, that in this case, we were interested in the nitric acid. So now we're ready to do our mole-to-mole relationship. And again, we hit another 1-to-1 here. A lot of those today, apparently. So we'll use our equation, and we can see that it is 1 mole of KOH gives us 1 mole of the nitric acid. So that's our third step, and that is really what's going to get us the moles of nitric acid. The moles of KOH will cancel, and we will now end up with 0.02475 moles of nitric acid, right? So we have now figured out the moles of nitric acid. So to figure out the volume, liters would be moles divided by molarity. And I'm going to use my molarity here of my nitric acid that was given to us as a conversion factor. Remember that opposites cancel, which means in this particular case, I actually need to put the moles on the bottom, which means I'm dividing by the molarity. And again, you don't have to worry about that if you just do dimensional analysis, because you'll know you should be dividing what's on the bottom, and those guys will cancel out. And we will end up with 0.165 liters of nitric acid, or if you want it in milliliters, 165 milliliters of nitric acid. You could get that by multiplying by 1,000 to convert it into milliliters, and you will end up with that. So again, you could use this conversion in the opposite way to convert it back there. So once again, we hopefully see our pattern of our 4 basic steps here. Once again, balance the equation, convert to moles, mole-to-mole relationship, and moles to some other unit. Any questions on that? You 100% should show the work like this through stoichiometry. You should not use an equation that people like to use oftentimes in titration situations, which is that dilution equation. Yeah, you should not use that here, even though you will get lucky on this one and you will get the right answer, but you will not get the right answer if it is not a one-to-one relationship. So even though people sometimes will call that the dilution, the titration equation, it really is not. It is only for dilution. It will only work if you have a one-to-one relationship between the acid and the base. If you don't, you will definitely get the wrong answer. So anything that involves titration, neutralization, you need to show stoichiometry here if you want all the credit. Do not use M1V1 equals M2V2 in this situation. Even though, again, you'll get lucky and you will get the right answer on this particular one, but it is not the proper way to show it. Any questions on that there? And you definitely will not get the right answer if it is not a one-to-one relationship between the acid and the base. All right. So why don't you try one here? What volume of 0.355 molar sodium hydroxide is required to react with 125 milliliters of 0.5 molar sulfuric acid? So take 3. Okay, let's take a look. See, so again, we have sodium hydroxide, which is a base. We have sulfuric acid, which obviously is an acid. So we definitely have an acid-base reaction happening here. and that's going to probably involve some stoichiometry. We should always know we get a salt and water. So sodium hydroxide, sodium is +1, hydroxide is -1. That gives us NaOH. Remember on the acid here, it does not have hydro, which means it does contain oxygen, and it ends in ic, which means we get rid of ic and put the 8 that goes with that. That is sulfate. And remember that all acids, the positive guy is H plus, so sulfuric acid is sulfate, which is SO4 2 minus. So you do need two hydrogens there, and that gets you H2SO4 as your acid sort of formula there. Any questions on that there? Hopefully review, I hope. So some sulfuric acid going to react with some sodium hydroxide. Again, in an acid-base reaction, it is a double displacement reaction. So once again, we're going to switch partners here on the other side. That is going to give us a salt, which is our sodium ion coming together with sulfate. So that's going to give us Na2SO4, as that is +1 and -2 coming together. So you need two sodiums. And of course, we're going to make water here, which is the result of, again, comboing our H plus from our acid and our OH minus from our base again to make our water, and our sodium and our sulfate here again making our salt as we switch partners. Any questions on that there? So again, want to make sure you have the proper formulas. You should not worry about balancing it until you get all the proper formulas down. Now you should definitely worry about balancing, and it looks like we might need a 2 there. And we will also perhaps need a 2 right about there, I think. So that'll give us 4 hydrogens on each side, 2 sodiums on each side, and 1 sulfate on each side. So it is balanced. So again, always want to do it in that order, proper formulas, then balance with coefficients. Now that we did that, we could look at sort of what information is given to us. And in this particular problem, we are looking for the volume of sodium hydroxide. We do know its molarity, which is 0.355 moles per liter. We are told that we're reacting 125 milliliters of our sulfuric acid, and we do know its molarity, which is 0.5 moles per liter as well. So the other thing we always want to look at when we're doing stoichiometry is it a limiting reagent situation? And this is not a limiting reagent situation, as we can only get moles of one of the reactants. And obviously, since we're trying to find something for the other reactant, there's no way to get there. So just a basic stoichiometry problem. So we obviously have our balance equation. We then want to convert to moles, and this is the only thing that we can convert moles to. Like normal, we do need to convert our volume into liters. So we're going to divide by 1,000 milliliters to a liter, 0.125 liters. So 0.125 liters using our molarity really as a conversion factor, 0.5 moles per liter of sulfuric acid in this case. The liters will cancel, and that's going to leave us moles. 0.125 times 0.5 gets us 0.0625 moles of sulfuric acid. And again, that is good because ultimately over here for our sodium hydroxide, we have to do something with molarity, and we are looking for the volume. We do have the molarity given to us. So once again, here we are using the stoichiometry to figure out the moles of sodium hydroxide so that we can use the molarity equation to figure out the volume. So again, that's where the stoichiometry part comes into play here, because we're not interested in sulfuric acid, but we are interested in that sodium hydroxide. So the third step would be to find the mole-to-mole relationship, and in this particular case, it is a 1 to 2 relationship from the equation. So for every 1 mole of sulfuric acid, you get actually 2 moles of sodium hydroxide. So finally not a 1-to-1 here. So we'll use that for our third step. 1 mole of sulfuric acid, 2 moles of sodium hydroxide. And we will end up with 0.125 moles of sodium hydroxide. So that was really the whole purpose of stoichiometry in this step, is for us to get to those moles of sodium hydroxide. Now that we have it, we could do our fourth step, which is really just rearranging the molarity equation. Now that we have this and solving for liters. So liters would be moles divided by the molarity. And again, we could also do a dimensional analysis sort of take on this. So we'll take our 0.125 moles of sodium hydroxide. Using the molarity here as a conversion factor, I could flip it upside down and put the moles on the bottom, which means I'm dividing by it, and our liters of sodium hydroxide. So again, just using the molarity as a conversion factor, that means, again, like normal, multiplying and dividing. Moles are going to cancel, and we will end up with here 0.355, 0.352 liters of sodium hydroxide. And if you multiply it by 1,000 to convert it into milliliters, you will end up with 352 milliliters of sodium hydroxide. And once again, you should hopefully see the 4 steps that we've been doing all semester long, pretty much. 1, 2, 3, and 4. Balance equation, convert to moles, mole to mole relationship, and moles into some other unit. Again, here, as you can see, instead of using the periodic table and molar mass like we did in previous problems, here we're using molarity actually in 2 steps. Up front here in step number 2, and in the very last step in step number 4 as well. We're just using molarity instead of the molar mass for periodic